Hi, everyone. I'm just getting things ready to set up for our next lesson. Let me scroll back through what we need. What we're looking at is from Unit 5, Chapter 4, where we've been focusing on oblique triangle trigonometry. And we're looking at Section 4.3 in this particular lesson, a very important lesson on the ambiguous case of the sine law. Now, what we tried to accomplish in this lesson was to help you understand what the ambiguous case actually involves and to give you something that you would be able to imagine what was going on so that you wouldn't have to memorize a set of rules, which is, of course, always a very more tedious way of doing something. But if you can imagine what this ambiguous case is about, then it helps you so much when you're trying to solve it with a triangle or with a word problem. So let's take a look at what we had. First of all, just laying some rules so that you understand the ambiguous case. When you're given information, and I'll describe for you in a minute what that particular information is, that creates a specific situation, we call it the ambiguous case of the sine law when you're faced with the possibility that you could have 0 triangles, 1 triangle, or 2 triangles. Now, ambiguous, just as a definition, means open to 2 or more interpretations. And so what's happening is you're given a scenario, and by its very nature, there's this possibility that you can have more than one answer. So the scenario is called SSA, or side-side angle. And we looked at that a little bit, drew it on the board. So we recognized that what it meant was we were given 2 sides of a triangle and an angle, making sure that the angle we were given was not the angle in between the 2 sides. So it could be on either end of those 2 sides. So you could say it's side-side angle or angle side-side. We can flip those when we're talking about this particular scenario. And what that also showed to us was that when we looked at it closely, we realized that another characteristic of this pattern is that you're given an angle, and by the nature of having side-side angle, you end up having the side opposite to that angle. So then we decided we would set up this manipulative, and we use this one in class to help us play with it a little bit. And just to explain it once again, what you had was a line along the bottom of your triangle that was an indefinite length. It would provide a variety of lengths as necessary. But what we were given was a rigid angle in the corner. We could call this angle A, I believe we called it in our example. This was rigid, it couldn't move. We were given this yellow side, which was also rigid, it would not move. And then we put it all together with this little tiny, short yellow geostrip in order to make a height that once again was consistent and would not change. But what we started to play with were these various lengths of geostrips, which we could twist around and move around to see what happened. Would they actually form a triangle or not? And what we used was this table in class, and we went through each scenario talking about what the short red geostrip length was with respect to the height, with respect to that side B, that yellow side. And then we talked about the number of triangles that it created. So let's go through the pictures one by one. And let's say the first one. We can see that this short red strip is less than the height. And if you can imagine twisting it over, it's also less than the side called B. And if you imagine swinging that back and forth, you'll realize that if this is my opposite side, opposite to this angle that I have in the corner, then this is definitely too short. It makes no triangle at all. The next one was for the blue strip. Once again, this side A, the new blue strip, is smaller than the height and smaller than the side called B. And when I swing it back and forth, I realize it does not make a triangle. The next one was exactly the same length as the height that we had. And so we could tell, all right, this one is it's equal to the height, but of course smaller than the side called B. But when I lay it over top, it makes exactly one triangle. and that is a triangle with a right angle in the corner. The next one we used was the next one in the strip, which was the white one. And when we twisted this one over, we realized it was longer, it's greater than the base, but it's still smaller than side B. And when we started to play around with it, we realized, okay, well, if we twist it over to this side, it makes this triangle. And if I twist it over to the left, it makes this triangle. So it makes two triangles. The next one is the B. And B is much longer than the height, but it's still a little bit shorter than side B. This one was the blue one. I might have said that funny, so just in case I did, go back and say that again. This is the blue strip. It is longer than the height, and it's shorter than side B. And once again, I can twist it around a little bit and realize if I have it over here, it's making this very skinny triangle, but it is a triangle. And then I can twist it over to the other side, and it makes one more. So we have two triangles. The last one was, you can see it tucked up in here, is the long red one. Oh, sorry, I skipped one. There is the yellow one first. And the yellow one, of course, is longer than the height, but it's equal to the side called B. Now, if it's equal to the side called B and I twisted this over, it overlaps on this one, and so there is no triangle anymore. It's simply an angle. The only way it will make a triangle is if I twist it over to this side, in which case it's making one triangle. And then lastly, with the side called red, which is definitely greater than the height, greater than the side called B, and I'd have to twist it over to this side, it makes one triangle. So then the challenge was to explain in your own words what you were seeing as you formed these triangles. Did you create one triangle? Did you create two triangles or no triangles? So we went back to our table and tried to understand what was happening. What was it that created no triangles? Well, that was when the side A was smaller than the height. There were no triangles. What was it that made one triangle? Well, when the side called A was exactly the same as the height, then we made one right triangle. And when the side called A was the same as the side called B or greater than, it made exactly one triangle. And then the time when it was making two triangles was when that side in the middle was greater than the height but smaller than the side called B, and then it would create two triangles. Now that led us to ask ourselves, okay, what's going to happen when our angle A, instead of being acute, becomes obtuse? And we drew an example of that one. So here's my angle in the corner. I'm calling it A. Here's my side called B. And this is my swing arm, or the side called A. Well, A is not going to create a triangle at all until it is longer than the side called B. Any other scenario, and there would be no triangle at all. There's also, if you have time to check out this source online, I would encourage you to do it. It's kind of fun. You can play with it. They've set it up so you can move things around and kind of scoot around with it just to see if you're understanding what they're talking about. So check it out. It's a good one. So remember, this is called the side-side angle. In our minds, we can also understand that it can be flipped to be angle side-side, which tends to be the one that we use more in our diagrams. Angle side-side, side-side angle. It's called the ambiguous case for sine law, or of the sine law. Now, what we did next was we went through it in a more mathematical way, and we tried to come up with naming each possibility. So I would encourage you to do this. If A is acute and A is less than H, there is no triangle. And you can see it, imagine it in your head. So again, as I go through each one of these, pause the video, imagine it yourself, and try to answer this, just to double check if you've managed to understand what we've been talking about. If A is acute and the side called A, is equal to H, there is exactly one right triangle. If A is acute and A is greater than the height, sorry, I said that wrong. So if A is exactly equal to, wait now, oh no, sorry, read what you have, Mrs. Darash. If A is acute And the cycle A is actually greater than the cycle B or equal to it, there is one triangle. If A is acute and A now is greater than the height, but it's smaller than the cycle B, this is the scenario which creates two triangles, two possibilities. You can see the one over on the left and the one using the side on the right. If A is obtuse and A is less than B or A is equal to B, there is no triangle at all. If A is obtuse and A is greater than B, there is one triangle. Okay, so that gets you ready to actually try some examples. So the first one we did is a very standard, straightforward one where we give you some scenarios of SSA. You're going to notice that all the angles are the same and all the bases are the same, and they are changing the sides called A. Now, in order to be able to really start to answer this, we need to know what the height is in this triangle. So the first thing we want to do as we look at this is figure out if my angle is 30 and my side is 12, what is my height? So over on the side, I use the primary ratio sine of 30 to figure out what the height was, and it turns out the height is 6 meters. Well, if A is 4 meters, then there is no triangle possible. If A is 6 meters, it's exactly the same as the height, then it creates one right triangle. If A is 8 meters, so now it's greater than the height, but it's smaller than the side called B, then that's the scenario where we have two possible triangles, one right here, this obtuse, and then this larger version. And lastly, if A is 15 meters, that means it's greater than the side called B, it will create exactly one triangle. Now, most of your homework for the first class was exactly this type of thing, and hopefully you were able to get it through checking the answers at the back and looking at my solutions. The lessons or the questions that you're going to do in the second part are more like the ones that are coming up, where it involves a word problem. So we managed to complete this one in class. Martina and Carl are part of a team that are studying weather patterns, the team is studying, watch my grammar. The team is about to launch a weather balloon to collect data. Martina's rope is 7.8 meters long and makes an angle of 36 degrees with the ground. Carl's rope is 5.9 meters. So, assuming they formed a triangle on a vertical plane with the weather balloon, what is the distance? Now, what we discussed in class was, what they don't tell us here is whether or not Martina and Carl are on the same side of the balloon or on opposite sides. They leave it ambiguous. And as soon as they do that, that should alert you to thinking, okay, maybe there are two possible answers here. So what we needed to do, first of all, was to figure out what is the height, because it's possible that Carl is standing on the opposite side of the balloon or on the same side of the balloon, if the height is right. Because right now, what we know about this side that we've been given is that it's 5.9. So first of all, we checked out the height and we realized it was only 4.6. So sure enough, both scenarios are possible. So that means we're going to need to go and take a look at those. So I'm going to go back to the triangle drawing so we get a sense of what we're doing. We're going to use, as we look at this, we're going to use the law of sines because, let's see where we are. We know this side and we're looking for an angle in this corner, but we know this angle in this side. So we're looking for the law of sines. The law of sines is going to give us our angle in this corner. Now remember, this angle in our particular scenario could be acute or obtuse. Now, if you think about what's going to happen, if you use the law of sines for this, then the law of sines is, and you use your calculator, it's going to give you the acute answer. It's going to give you this one. So to be able to find the other one, you're going to have to use the supplement of the angle to find this second one. And sure enough, when you look at the work, it actually gives you an angle, and you can set it up here, of, let's say, 51 degrees. But since angle C is also obtuse, that means it could also be 129 degrees. So then you have your two scenarios. You've got this one where it's 51 and this one where it's 129. And I have to apologize because I did not have the work actually drawn for this. So I didn't finish the question. We did it in class where we needed to find the length of these sides, but I don't have it to put in front of you. So let's just talk it through. If we know this is 51 degrees, then we need to find our third angle. We can use angle sum to find that, 36 and 51 minus the 180, or from 180 is what I should say. That sets me up perfectly to use the law of cosines to be able to find the distance of these two people. And so go ahead and use that and find your distance. For this one, same thing, although we have a different angle and it was 129, so that means our third angle is going to be different. But that sets us up perfectly to use the law of cosines so that we can find the distance between Martina and Carl. Now, this question. When we worked on it in class, most classes didn't have enough time. We tried to take a look at this and draw it. And when we were working on it in one of the blocks, we realized that there's a bit of an issue going on in here. And what I want to point out to you is that they talk about walking northwest. Now, I've done some research on that, and we went with the assumption as well that northwest was exactly halfway between north and west, so the 45 degrees west. And we are right in doing that. However, if you were to look at the solution for this one online in the text, they leave that and leave it open for interpretation and basically sort of have the person going basically in a northwest-ish direction. And they go with trying to solve the question without knowing that angle. Now, that gives you two different scenarios. And so it's a bit of a glitch, I think, within this question. It must have been that they did not technically understand this to be north 45 degrees west. But we went with that assumption in class. It made the question a lot easier. We were able to find it. So I did some research on it and just looked around and realized, no, we were not wrong in that. But it must have been in this context that they meant to leave it vague. So let's take a look at what it would look like if it was vague. Basically, they had this kind of a scenario. They knew that they walked 12.4. They knew that they walked 7 to the lake. They knew that the angle was 30 degrees, and that's all they used. So what we're looking at here is an angle side-side or the side-side angle scenario. So if we're going to use the law of sines, which is a natural one, remember that you're going to have two possible scenarios of the angles that you're being shown. From our diagram, it is clear that we are using the obtuse angle. But if we use the law of sines here, we're going to be given the acute angle. And so we need to compensate for that, make sure that we use the obtuse one or find it, and go on with our question. So here you have it. This is me using the law of sines. This is the angle that comes out basically 62. And then, but since the angle is obviously obtuse in our particular scenario, the angle is really 118. And once we understand that it's 118, and we know that it's 118 right here, and that we need to subtract 90 from it, that gives us our answer of having to go south 62 degrees east. And so if we look back at the diagram once again, basically I wanted to know what this angle was. And so probably what would have been better than figuring out this little guy and figuring out another one would be to take 180 and subtract the 118 to get the 62. So I hope that clarifies that question for you. It was a bit of an unusual one. And so hopefully that will set you so that you're in a good place to finish the rest of your assignment. Good luck, everybody, with your work and with the ambiguous case. This would be your homework for the second part of the second day. Okay, take care.